I'm doing a few tests, spot welding 0.1mm thick nickel strip to some scrap sub C cells. I'm using 1/16 of an inch diameter glidcop tips at a center-to-center distance of 0.17 inches with a tip pressure of around 5 pounds. The 5 to 20 volt weld pulses are supplied by my work-in-progress capacitor discharge welder. I'm going to start with what I think was the best weld overall, at least the one with the most difficult to remove tab. Some of the higher powered welds had bigger weld nuggets, but the melting of the nickel around the weld made them easier to pull off. Here is the waveform of the 11 volt 10 millisecond weld pulse. The yellow trace is the top of the MOSFET switch bus. The green trace is the positive bus of the capacitors. The red trace is the terminal of the right tip holder. The blue trace is the terminal of the left tip holder. The difference between the green and red trace is 24 inches of 4-gauge copper wire with a resistance of about 0.5 milliohms. The difference between the yellow trace and the blue trace is another 24 inches of 4-gauge wire. One thing that stands out from the waveform, I am wasting a lot of energy in the two leads. If only 60% of 80 joules went to the weld tips, I'm going to say it takes about 50 joules at the weld tips to get a good weld on 0.1mm thick nickel strip. I think this green trace section here represents the resistance of the capacitors, maybe a little less than 1.5 milliohms, and that is less than I was expecting. I'm going to refer to these welds by the energy I think is going to the tips. So this is the 40 joule test. The weld is very close to the 50 joule one. The weld nuggets are just a bit smaller, but it still seems to be a good strong weld. This one is close to 60 joules, and the nickel is softening some with quite a bit more tip impression on the tab. The weld nuggets are a little larger, but the tab pulls off easier, as the nickel seems to tear easier at the edge of the weld. It could be it is a better electrical weld, but weaker mechanically. Now for some of the welds that didn't work too well. With less than 20 joules, there were no weld nuggets at all. The tab pulled off easy with only a little bit of stick at the welds. And this is what the waveform looked like for this 7 volt 10 millisecond weld pulse. At about 25 joules, there starts to be some weld nuggets. The tab pulls off easy, and there is one small and one very, very tiny nugget. A little more power and they get a little bigger. The nuggets do increase in size till power gets up to around 90 joules, and then it's kind of hard to tell the size or even if it is a nugget or just melted metal. When we get to around 70 joules, I think this is just too much weld energy. There is now a little bit of a crater at one of the welds, and the nickel really tears quite easily at the weld. Though the nuggets look quite good, there is not much vertical height to them. At about 90 joules, both welds are a little cratered and melted. When we get to the 110 joules, with a 20 volt 3 millisecond pulse, the edges of the welds look very melted. When we move up to 20 volts and a 5 millisecond pulse, it just blows the metal out and takes some of the electrode tip with it. The waveform shows that it used less than the 110 joules of the previous weld, but the initial intensity must have been enough to vaporize some of the metal and create an arc. At least I think that is what the waveform looks like as it is arcing. So it is not just the total energy delivered to the weld, but the shape of the energy as well. Even with this one using less energy, it made by far the deepest crater in the steel.